In this video, we're going to look at a few problems from topic 8, testing a claim about two population proportions. So compared to the last two types of hypothesis tests that we've done, this one is a little bit more tame in terms of any kind of weird flares it could have. So if we look at the reference tables, we have the same null and alternative hypothesis setup that we have been looking at. And then we have the same extension from a one sample to a two sample test as we did with standard deviations and means. So we need both of the samples to be random in a perfect world. We need the samples to be independent, ideally. However, if this fails again, we kind of keep it as a disclaimer in mind. It's not a reason to stop doing the test. However, having 5 successes and 5 failures for each sample, that is absolutely crucial in order for this test to hold up. So again, proportions follow the z-distribution. Although SATA does give you the z-score, this is the calculation for the z-score if you did want to find it. You'd actually need to look up how to find p-bar and q-bar, but I don't imagine anyone would want to do this by hand when SATA so easily gives it to us. And then we're going to be selecting the proportion test calculator for every problem. Because even if you're doing your project on a 1 or 2 population proportion, you're going to have your data summarized because that's kind of naturally what happens when you do proportion data. So another thing that I want to outline is that proportion data is actually categorical. So we'll talk about that with our first problem. So this is actually a slightly unusual use of statistics. But in a recent World Series, the Houston Astros were ordered to keep the roof of their stadium open. The Houston team claimed that this would make them lose their home team advantage because the noise from fans would be less effective. During the regular season, Houston won 36 out of 53 games with the roof closed and 15 out of 26 with the roof open. Use a .05 significance level to test the claim that the proportion of wins at home is statistically higher with the roof closed than with the roof open. So using statistics with this data, because this is a census, is actually only necessary if you want to show that there is a statistical difference. If you want to just show that their proportion of wins is higher with the roof closed, well, we don't need to do that because it is just higher if you're comparing the two numbers. However, they're saying that it makes a big difference in their game, so they are going to be saying that this difference is big enough to be statistically different. Well, first of all, I can already tell that going into this problem, because of sample sizes with proportions, we're not going to have a big enough sample size here to be able to tell a difference between 10%. And so we'll see when we get to step 7. If I was this team, I would, demand to maybe use a few more previous seasons and argue that the cohort of players, although different, would be pretty similar for, the few years before the World Series as well. But that's another reason why I like this problem, is it details how hard it is for proportions to have a small width in their confidence intervals in order to be able to tell a difference between something like 10%. So the way that I would, again, start off this problem is the exact same way that I would, start off any of the previous problems. And I usually take whatever population is stated first as the one that I write first. So we're going to test the claim that the proportion of wins at home is higher than with the roof closed than open. So I put that the proportion of the closed roof is greater than the proportion of wins with the open roof. So that's going to be our H1, and our HO is going to be the same thing with an equal sign. And then I already went over my census disclaimer. Because remember, if we're just trying to tell if they have a higher proportion of wins at home with the roof closed, well, this is true. So for that season, they definitely have won more with the roof closed. However, how do we know this isn't just luck? How do we know is this big enough of a difference to say that, okay, they're definitely, winning more with the roof closed because of, the home field advantage crowd noise. So I don't think this is big of a difference at all, especially when you consider all of the variables that can come into play for, the success or failure of a baseball game. So I'll talk about that a little bit more with our assumptions. So random, this is actually better than random because this is a census of that whole year. So again, using a census in statistics is kind of weird unless you're generalizing beyond your sample data or your census data. Or in this case, we want to see if the difference is big enough to be statistically different. So independence, I think this would fail pretty hard here because, I mean, the games are consecutive. They are going to be, having 4 games home, 4 games away, or, whatever their schedule is like. So if they're doing a day after travel, they might be maybe a little bit more tired. That could affect their playing. Pitching is a big deal. So, for all these games, they're not going to have the same pitchers. So in a way, you can choose to account for every single detail or just kind of say, well, the situation is kind of going to even itself out over the all of the home games. So that would be something I would open up for somebody that knows more about baseball than myself, which is the cool thing about statistics. You don't need to know a lot about the exact topic. You can still run any kind of test on it once you understand the problem well enough. We do have 5 successes and 5 failures for each sample. So again, if this one fails, you do have to actually stop the test. It's not going to be strong enough to run the test at all. Your confidence interval would be so wide it could span, 60, 70%. So maybe it could be, the win is from 20% to 90%. So, I mean, that's really not saying anything at all because the confidence interval would be so huge. So when we go to put this in Stata, we're going to select the proportion test calculator. And we have a sample size of 53 for the roof closed and a sample size of 26 with the roof open. And then our proportion is not 36 and 15. It would actually be the 0.6792 and 0.5769 unless we check this box, and then it's okay for us to put in counts here instead of the actual decimal value. So this is going to be a right-tailed test. So whatever alpha is, we're going to have to double that tail. So we have 0.05, we're going to need to double that to be 1 in one tail, 1 in another. So this is going to be at the 90% level. And so then when you hit OK, we end up getting a z-score of 0.89, which is pretty close to the middle. So I'm expecting a pretty high p-value, 0.1858. And then our confidence interval, negative 0.0888 to positive 0.2934. So that's what I have here. And so this p-value is higher than any alpha that you would ever set. So that's going to be, the p is high. We're going to fail to reject HO, so the HO will fly. And so if we're going with HO, then that means we're going to reject H1, and that's also our claim. So we're going to reject the claim that the proportion of wins with the roof closed is statistically higher than with the roof open. So that's not true based on this data. However, I mean, anyone who has dealt with a lot of proportion data will already know that sample sizes are very weak. So what I'm actually going to do is I'm just going to show what would happen if we had 10 times this proportion. So let's say that instead of, so I'm going to use these unrounded proportions. So closed is 0.6792, open is 0.5769. But let's say they ended up using 10 seasons. They went back the last 10 seasons to see if that kind of cohort of players was having higher wins. Well, if that were the case, so this is purely hypothetical, we would end up being able to say that there is a statistical difference because we have a lot more confidence that these proportions are going to be true since we have a lot more data to support that. So, and again, the z-score formula that is used to calculate this is based on the the sample size in this case. With means and standard deviations, however, it's based on the sample size as well as, the mean and standard deviation, or just the standard deviation. So we have, instead of just a sample proportion with a sample size, we have more than just one statistic to base our results off from. So that's why means and standard deviations aren't as weak to sample size, because they're based off from, more summary values. So our picture, remember, right in the middle, saying that the two are statistically the same is also that there's evidence they're statistically equal to 0. So if they were the same exact proportion and we subtracted them, they would be 0. However, these two are going to be based off from confidence intervals instead of just a single summary value. So this z-score would be on the positive side, and it's going to be around 20%. So I don't think that's too bad. Maybe it's a little too big, but as long as you're kind of in the ballpark, pun intended. So this shaded area is on the right side because we have a greater than over here. And then our confidence interval. So I usually interpret this in two ways. The first is, the only thing you have to say is that since 0 is inside the confidence interval, this supports failing to reject HO. So this confidence interval goes from negative to positive. So that means that since there's a sign change, there has to be 0 inside if you think about this on a number line. So the way we'd interpret this is that at the 90% level, there is 8.88% less wins to 29.34% more wins with the roof closed than with the roof open. So there's no evidence to suggest right now that it's anything different than 0. So the rest of these tests are pretty standard. So I want to try to have you guys attempt more problems independently, especially since this section doesn't have many quirks at all, and the Stata use is actually pretty nice. On this second problem, it seems kind of messed up, but it is actually what happened when Jonas Salk was coming up with the polio vaccine. So this one has a little challenge in that the proportions are really small. So be careful with that one. Number 3 is one of my favorite problems of the semester. So I'm going to give you a hint on this though. So when setting up this problem, you want to ask yourself, what are the comparisons that we want to make? So that's going to help you decide which way you go, whether you go up and down in the table or whether you go across in the rows. So I would take a second to pause this and ask yourself, what are the two groups we want to compare and what is a success? So that will lead you to decide whether you want to go up or down or go across the rows. Because sometimes people just automatically go across the rows and say, oh, okay, my sample size is going to be these two added together or these two added together. Or they go the other direction. So this one you actually have to think about. It's very interesting, and there's a lot of things about this problem that I would also want to know. So other things that could be predictive of whether or not someone is sentenced to prison besides just their previous arrest record. And then this last problem is going to have a high p-value, so don't stress out, but I recommend finding the sample proportions in order to convince yourself that that high p-value makes sense. So if you have any questions, please feel free to send me an email. And remember, this test is very tame and it doesn't have as many quirks as the last one. So when you are setting these problems up, just set up the 7 steps and go through them exactly how we would have before. And then the Stata, the big thing with that one is the checkbox. So if anything goes wrong with Stata, it will give you some kind of error. And sometimes the error is helpful with helping you decide what went wrong, and sometimes it's not. So if you have any questions, send me an email.